Yeah. Good morning, everyone. My name is Davide Grassano, and I'm also a material scientist turned quite recently into software developer, and I'm currently working at the EUM' Center for Atomic and Molecular Calculation situated in. And today I'm going to talk about some of the recent effort in developing a new LLVM toolchain for EasyBuild. A brief outline, but I would say let's go right into it with just a few small design concepts for modern compilers. In general, modern compilers relies a lot on intermediate representation, which is basically any data structure that can represent the original program without any loss of, ideally without any loss of information. These are usually divided into either in a modular way or just logically into three subunits, which are the front end, the middle end, and the back end. The front end is what is responsible for ingesting the source language, perform parsing, lexical analysis, abstract syntax tree, which is either transformed into another intermediate representation or pass as is to the middle end. The middle end will then perform some generic code optimization and will spit out another intermediate representation, which can be either a different form of the ingested one or the same one, as we will see. And this will go into the backend, which is the part of the compiler responsible for the actual code generation and target specific optimizations. As an example, this is how a typical GCC workflow goes on, slightly exemplified. You have your, for example, your C program, it will go through the C preprocessor, and then it will go into the front end of GCC, which will parse the code and transform it into an abstract syntax tree. This will be then passed to the middle end, and you will go through the first of three intermediate representation, which is called generic, and then through a series of tightly interconnected transformation and passes, your code will go through Gimple, which is another intermediate representation, or also known as, and then it will go through Gimple SSA, and throughout all these passes, there will be a lot of optimization that are done for your code, and one of the aims of Gimple is to be fairly simple, is that it implements as little number of instructions possible, and it tends to enable fairly aggressive optimization. Once we are done with the middle end, we will actually go to another intermediate representation, which is known as register transfer language, which is what GCC uses to perform the target optimization. Now, recently, I mean, not so recently, but quite recently, there is been this new of compilers, which is a project that has been adopted a lot, as we will see. And basically, this project is a collection of modular and reusable compiler toolchains and technologies. This is literally the page. And basically, this is a project that started in the year 2000 in the University of Illinois, and it was originally, LLVM originally was an acronym for low-level virtual machine. Interestingly, this is not the case anymore since 2011, as this acronym didn't represent what the project stood for anymore. And it was basically started by Vikram Adve and Chris Lattner, which had its first release in 2003. And then in 2005, the project went on to by the Apple, the title Chris Lattner, and they kept working on it in order to integrate it into the Xcode iOS. And since 2007, LLVM actually had its first standalone compiler. Before, it was actually relying on a plugin for GCC to spit out R, which is the intermediate representation used by LLVM. The code optimization and generation. So what is the philosophy behind LLVM? One of the main philosophies is to decouple the front end from the front end operation from the back end operation. And in LLVM, this is achieved by the completeness of the intermediate representation. Basically, we want the idea of the LLVM IR is to be able to represent as much as possible every operation that we as source language we want to do, and any operation that should be target specific. And in this way, basically, LLVM uses only one intermediate representation. So the optimization will start from LLVM IR and will spit out other LLVM IR just optimized. And this, together with the modularization of the project, which is organized as a set of library with an API that you can look into, allows all the components of this compiler to be reusable. So you can either design a new front end that spit out LLVM IR and then reuse all the middle and then backend to do the code optimization and generation. You can also hook into the middle end by writing your own custom passes, for example. And this is in general highly extensible and customizable. And this is a list of projects that are actually in the LLVM project. A few of the most relevant ones, I mean, they're all important, but I would say the one I would stress are the LLVM core, which basically implements LLVM IR and the backend with the target code generation. There is the C++ front and Clang. There is an integrated debugger LLDB, and there are some runtimes that implement the C++ and C standard library, as we will see later. Level of completeness yet. And then there are more runtimes. There is MLIR, which is basically another IR built on top of LLVM. It's built to target LLVM IR, and basically it's the basis of a lot of new machine learning compilers, and it is also what the Flang front end is built on top of. And yeah, so finally I would say Flang, it's what we were basically waiting on before we started working on an LLVM toolchain. This is because we cannot really go in an HPC environment with a toolchain that doesn't. This is fairly probably very non-comprehensive list of frontends and toolchain that use LLVM under the hood in one. Another is either they use it as is to perform just-in-time compilation, or they have their own fork with some modification. And we already saw a little bit about this yesterday, but this is a simplified timeline of the development of Flang and how it was ported into it. I will not go into all the details, but basically it's a project that started in the PGI group, I think slightly before it was acquired by NVIDIA in 2015. And while this original project kept going on and being developed as what is now known as Classic Flang, in 2018 it started being upstream into the LLVM project and went under many modifications. And it's basically now a totally different compiler that does not target LLVM IR directly, but build first on top of MLIR with another two intermediate representation. The original was FIR, which is Fortran IR, and then there is also HLFIR, which is high-level Fortran. And basically after 10 years, basically 3 or 4 weeks ago, we got the release of LLVM 20.1.0, where we actually have the first Fortran compiler in LLVM. And there is also the renaming that you have already heard from Flang new to Flang, which, as we will see, can cause some problem with build systems. This is basically the workflow that a Fortran code with OpenMP will go through. For example, we're compiling up to LLVM IR. We basically need, first of all, to perform the parsing. Then we will have an intermediate representation, which is a mix of dialect of HLF FIR, and OpenMP dialect. This will be the HL FIR will be all lower to FIR, and then the MLR will be actually transformed into LLVM IR, also making use of the OpenMP IR builder to actually have all the OpenMP stuff in the way it is implemented. Another interesting workflow that I think is worth noting is what happens when you do a compilation with offloading. When you are compiling with offloading, you are basically compiling multiple times your executable, once for the host and many times for all the devices that you want to target. And this usually also relies on other runtimes that are offered by LLVM and possibly by tooling that is specific for the target to generate the executable code. This is an example for an NVIDIA GPU where you are basically compiling your host code and then you're compiling in parallel for your GPU, and you can either spit out PTX code as is and then go with just-in-time compilation, or further compile it down to SAS and then link everything into a executable. This is an example of, and also to show the reusability of some of the components of what happens when we want to compile with Flang and offloading. This is just a simple Hello World OpenMP program, and we are compiling it with OpenMP, and we are targeting, in this case, the host architecture head on my workstation. So for simplicity, I just went with this. And if we run this command with the -v flag, LLVM will actually tell us all the compiler driver invocation that happens in between, which is very nice. The first step is basically to compile for the host target and to lower the OpenMP code to metadata annotated LLVM IR node. This metadata will be used by another pass of Flang to start compiling the device code, and this then we'll go through the some tooling that was already made for Clang, which is the Clang offload packager, and it will produce an image file that will be embedded into a new elf section of the object file being produced by another Flang pass. At this stage, the host code and the device code can still not talk to each other because they're not aware of counterparts. So you actually need to go through another set of tooling, which is also what Clang uses under the hood to do the offload packaging. And it is to go through Clang linker wrapper, which is basically the responsibility of extracting the device code, and then it will invoke Clang to wrap basically all the offload entries and symbols in a way that can be accessed by the host. And then it will actually perform two steps of linking, one for the host and one for the device, to then give us the final fat binary that can be run on actual offloading going on. Now, on to the actual effort to produce a toolchain. The first thing that needed to be done was to basically rewrite the EasyBlock. Before this effort, we had a lot of EasyBlocks, including LLVM. The two major ones were the LLVM one, which was targeting just LLVM core, so you were just getting the LLVM middle and backend, and without any of the front end or other tooling. And then there was the Clang EasyBlock, which did not support for shared libraries, and originally was just meant for Clang, but it was actually extended to build also other projects, but still was missing several features that we wanted to implement for the new LLVM EasyBlock. And at the end, we decided not to extend Clang or LLVM independently, but to fuse the two EasyBlock into what is basically now the new LLVM EasyBlock that has been merged into EasyBuild 5.0. And this new EasyBlock basically allows both for static and share build of LLVM and all of its components. It allows for a minimal build, which is basically a compatibility mode with the old LLVM EasyBlock, where we are just building core. It allows either building on top of GCC or any other compiler that if you're feeling adventurous, or in full LLVM mode. Full LLVM basically means that you start from a compiler that you have under your end, but the final compiler and set of library should be independent from what was given as an input, and this could be useful if we want to have a totally independent toolchain. And this is also a point of discussion that we will see later in the slides. It allows for a more detailed project configuration, and now we are actually running the test suite. Before the test suite was there, but as far as I know, it was basically disabled in all the Clang easy config files that were. So a few of the challenges encountered during this process. I would say one of the nice things of the LLVM test suite is that it is highly extensible and configurable. One of the cons of the LLVM test suite is also that it is highly extensible and configurable because the default configuration makes some assumption in where some libraries are going to be found and other stuff about your system, and this is not always true in general. For example, while I was working on my workstation, everything was working fine, but when we went to the EasyBuild build cluster and libatomic could not be found in the standard system path, we actually basically had we were not able to run the test suite, and the way to work around it, some of it could be done through CMake parameters at the configure step, but most of it actually is patches to the configure file that are made available by default in the LLVM test suite. So we are ensuring, for example, that you are passing LD library path where it was not necessarily being passed because they thought it was not useful, or we are doing configuration to properly detect the target triples in the part of the test suite. And after a lot of work, this is the current status of running the LLVM test suite after compilation. This is for the, actually not anymore the latest because there is 20.1.1, but this is for 20.1. Here is when we are compiling for host only. We are basically running 72-73% of the test suite. The rest is unsupported because we are compiling only for the host architecture. And we end up only with 5 errors and 2 timeouts, which after some investigation, they are basically not going to affect the functionality of the compiler afterwards. Some of them might actually be some bugs or still stuff that should be ironed out in the way we are patching the configuration file, but it's not too much of a worry. And just last week, I also tried to build on my machine for all targets, and I was expecting a much worse results. So I was happy when basically we went from 5 errors to just 12. 6 of which I think might be either related to some flags we're missing for compiling for PowerPC, or actually some configuration that also need to patch out for this part, because basically this test we're failing to find the correct headers for the target triple. And then there is another failure that is because we are not using Google test, but find it. So I would say we are still doing pretty fine here. Another one of the main challenges was ensuring our path was working correctly for LLVM, and we made an effort for this, especially since this is now the default in EasyBuild 5. And actually it was thanks to EasyBuild 5 more aggressive checks on when you have our path enabled that we found out that you actually had a problem. This is basically a schematization of how LLVM is built. It is in general, you go to 3 stages where you start from your system dependencies, and then you start with an interplay of system plus LLVM dependencies. And after the stage 3, you can get the full LLVM without any of the original, with the full interplay between the project and the runtimes. The problem here is that basically, as you can see, you go in with your system compiler, you run your configuration. Here you have your RPath wrappers that are produced by EasyBuild, so you will actually be using them. The problem is that when you start the build, everything in the red block is what the make invocation does. So it does the project builds, so it builds the compiler and some libraries, and then it takes the compiler that were produced and pass them to another CMake invocation to build the runtimes. Here you can see the problem is that at this point we are not using the RPath version of the compiler anymore, we are just using the bare one that we're producing. And this meant that the runtimes library and now since 19 also some UTD binary that were produced were actually not correctly RPathed. We were able to fix it. It is a slightly hackish way, and it relies on the fact that we can pass some flag from this CMake invocation to this CMake invocation, but we either need to patch out the fact that this CMake invocation is taking the compiler from here, or we rely on the fact that the flags that we are passing from here are actually happening later in the command line invocation for CMake. And if you pass the same argument to CMake twice, the one that counts actually is the last one. And this might not be stable behavior, or we might need to be careful when we update the LLVM, the CMake dependency for LLVM, but this is the way we solve the problem for now. So now on to building the toolchain. First problem, naming scheme. And here I'm very open to suggestion. I just took the easy route of adding L to LFOS, and actually Alan pointed out that it could have been funnier going with floss instead of elfos. And yeah, then it was just replacing the G with an L wherever there was the G for GNU, and just this minor recap of having to add the TC to LLVM to distinguish it for the EasyBlock and EasyConfig names. So after deciding on a name to use, what do we do? Do we start to rewrite literally every EasyConfig file with the new toolchain? Ideally, this is what we are going to have to do at the end, but that's not ideal for testing because otherwise we're going to go crazy. For this, we can leverage the very nice option that EasyBuild offers, that is try toolchain. We can basically take an EasyConfig that already exists and try to compile it with a different toolchain, and EasyBuild will take care of substituting the toolchain wherever it is needed. In particular, this also works with the -robot option. So this means that if we are compiling at the, let's say we are compiling a FOSS EasyConfig and we want to replace it with LFOSS. If we are compiling a dependency that depends on a sub toolchain, try toolchain will actually replace it with the correct equivalent sub toolchain. And if you try to run the list of dependencies needed with try toolchain without actually having compiled them, it will not work. But you can actually get the full list of dependencies after you have compiled them. And this is actually highlighted in red, not the top one because this is some no EasyConfig found, but these are the actually EasyConfig that I had to rewrite manually in order to make the toolchain working and going up to Quantum Espresso, as we will see. So let's start actually doing the work for the toolchain. First of all, we need to add the toolchain definition to framework. To do this, I basically took the definition of the FOSS toolchain, copied it, did the renaming, and didn't have to touch much else about it besides the fact that Flang still does not support all the compiler options that Clang does. And so I had to do some more granular splitting or the way we are passing the option at the core level of the toolchain, but this was basically the modification needed for now. So let's start building the toolchain. Now, first problem, in order to have total feature parity with the FOSS toolchain, and to not have all the EasyConfigs complain about missing dependency, we actually have to include BNuDis. The problem is this: if you try to compile BNuDis with LLVM, we will actually get a lot of error, which I didn't even bother to investigate, because LLVM has its own version of BNuDis that is coming with LLVM core. So you either write a module file to make EasyBuild think, okay, you have already installed BNuDis, you're good to go, or in my case, I just made an empty EasyConfig. By empty, I mean I use a bundle EasyConfig that was bundling a file going. So not much problem here. Then we hope to get at least 3 or 4 EasyConfig in. Unfortunately, if scaring me and making me think this was going to be a lot of work, first EasyConfig we try to go actually compile, zlib, we get a problem. But this was not too bad because it was just a difference in the version where the LLVM linker does not enable undefined version script or linking by default. And we solved this by adding this to this flag to the C flag, and I actually made these toolchain options because we want the LLVM toolchain to behave as closely as possible to the GCC one for all cases. And after doing this, I basically never encountered a problem related to this again. Might be that some other EasyConfig needs this flag. We can just put it all the time. It's not really a problem, at least not as far as I've experienced. Then we actually go quite far in compiling the toolchain. We go through the linear algebra enabled toolchain, so LFBF. We basically compile everything. The first problem we encounter, and this is a kind of problem that will be probably the most relevant for all the other packages, is that it's related to the compiler definition. If you try to compile FFTW with quad precision, there is actually a check in the configure script that your compiler needs to be GCC greater than 4.6. Now you might say, we are using a very new version of LLVM built on top of GCC 13. Whatever. Why are we not passing this check? Is because this is checking for GCC greater than 4.6. So when we get the compiler definition from LLVM, it actually does not match and is failing this check. Easy solution, just do not compile with quad precision, or we will patch this in, but I decided to go with not compiling with quad precision because if you actually look in the easy block for FFTW, when you compile the MPI version, it disables quad precision by default. So I just say why include it in the non-MPI one. And it compiled fine, it passed the test suite. And then actually we also got, we could compile OpenBlast and FlexiBlast without much trouble. The only thing I think might be something with toolchain, but there was a problem with the extension in FlexiBlast. I just had to recreate the easy config, substitute the toolchain, and it worked, so not much there. Then we moved toward the OpenMPI enabled toolchain. First problem was a compatibility problem with UCX, but it was actually a known one, just a little bit of searching, and this is because I was building starting from the 2024A FOSS toolchain, and here the UCX version used was actually 1.16, so it's either bump the UCX version up or apply the patch that was made to fix this problem. In this case, to avoid having to change the UCX dependencies in all the other easy config, I just applied the patch, but in the future we can just version of UCX. Then problem with libpci access was just some more aggressive error checking by LLVM, and it was found the combination with W error was triggering some error due to the warning of int conversion. So in this case, I just passed the -w in conversion flag. Now, one easy config that I actually haven't managed to get it done yet is the HDFI one, and here there was actually a couple of funny problems. One of the things that the configure script of HDF5 does, it's first run the Fortran compiler in a kind of dry run mode to get some of the flag that you will pass further on in the compilation. The problem is that when you do this with march native with flang, among the flag that it gives you, it will actually be this -target feature -LWP. And these flags are also being used for Clang. And the problem is that Clang does not recognize this target feature flag and thinks that -WLP is actually a library. So this was a quite annoying one to find. We'll say, what is this WLP library? Where is this coming from? So I basically had to debug the entire config script to see that I was doing this thing with Clang. Another thing that the HDF5 does is gives you a wrapped around version of the compiler that you're using that are HDF5 aware. You produce, like, for example, this H5CC. And in doing this, it is nice enough to keep the original compiler description that you get from -- version. The problem is that it does so by injecting the compiler description in the C file into a string. What happens if your compiler description includes double commas that are not escaped? So I guess here we can open a new CV of code injection by compiler description. that will be a fun one. And after that, I decided, okay, I want to try to at least get to some scientific code for this presentation. So I stopped working on HDF5 and decided to go with QE without HDF5. Then we moved toward the actual LFOS toolchain. All the other problem was the fact that Scalapack was giving some undeclared function error, and this was just about setting the C standard to 89. So I guess that fixed it. And now another class of problem that might be more or less relevant depending on how old the Fortran code you're trying to compile is and how crazy the developer went with pre-compiler macros. There is actually some difference in the behavior of the G-Fortran pre-compiler and the Clang one. Some of them are being fixed. For example, this one, they basically defining the same function with different name by using a pre-compiler macro, and they use this by doing this multi-line syntax. The problem is this was not being parsed correctly by the Flang pre-compiler, and this was not being replaced. Turns out you can fix it by just removing the space between these two % for Flang, and it worked. And I tried to patch it out and move forward. There was actually a patch that I think might be in 20.1 for this. And another problem due to pre-compiler macros, another thing they do in the LPAS library is actually also write custom strings depending on pre-compiler macros, and here they even go more crazy. They start to go with if basis for the pre-compiler, and here Flang just said, okay, I'm finding a string that is unterminated. And at this point I decided, okay, let's try to compile Quantum Espresso without help and wait for this problem to be fixed in the compiler. So at this point we are basically ready. We compile libxc, passing the test suite, here all good. So we try to compile Quantum Espresso. And we start to hit this problem. Now, I think Jeff might recognize this because he actually talked about this, and this is a problem due to the ignored TKR not being either properly set or properly recognized. And at the beginning, I spent quite some time thinking this was a problem with Quantum Espresso and the Fortran standard because non-contiguous array were in the 2008 standard, but actually it's just an incompatibility. After more digging, it is just an incompatibility between LLVM greater than 19 and OpenMPI lower than 5.0.4. And fun fact, we started starting from the FOSS 2024 toolchain, the version of OpenMPI was 5.0.3. Lucky there, and we ended up finding this bug, but it was just about bumping up the version of OpenMPI. We rebuild everything that depend on it, and we compile again. And now here we actually start to get in some LLVM specific problem. Now the status of Fortran in LLVM is pretty good, but there are still some missing features. And here we are actually hitting one for the D3Q plugin for Quantum Espresso. And basically, when you get these errors, we will show more later. But it's basically some functions that are in the code generation or IR lowering in LLVM, and when you hit them, it will just say this feature is not implemented. We cannot go further. After removing the 3Q plugin, at least we managed to compile Quantum Espresso, and surprisingly, we are also passing the test suite with 100%. Before, we were actually, when we were doing this with FOSS, we actually had to ignore some failure due to there are some flaky tests in QE where they're doing some relaxation, and I think the convergence threshold they're setting for the result they expect with the one you get are probably too strict. And this is a known problem in general when you're doing a relaxation calculation with low convergence parameters, but that's... So in this case, we are actually going with 100%, and the guess is because the original test suite in QE is meant as like the original result had been done with an Intel compiler, which I guess they did it them under the hood, so maybe they are behaving more similarly to the GCC one. Investigate further why that was the case. And as far as performance goes, I did a small, I ran the different tests that we have implemented also in the easy test on my workstation, both for the FOSS 2024A and the new FOSS 2025A, and they're actually quite comparable. The LLVM one is a few percent slower, but we still haven't tested out all the possible optimization that are specific to LLVM. And this is actually in line with other benchmark that I found online where they compare actually the latest release of LLVM with the year to come 15.0, where sometimes LLVM is faster, sometimes GCC is faster. On average, GCC still tend to be a few percent faster, but the comparison in terms of performance of compiled code is getting very close between the two compilers. Now, I will not go too much into the details here, but basically I also attempted to compile CP2K, ended up encountering some problem with Rust for compiling the SciPy bundle, and this is because Rust uses its own internal version of LLVM, and if you try to compile a Rust that depends, for example, on LLVM 19, using LLVM 20, I was just getting some symbol clashes, and you can actually compile a Rust that depends on LLVM 19 there, but this means there might be some interplay between the libraries that Rust compiles and the one that LLVM compiles, and this needs more investigation. I ended up punching around a lot the Meson build system to make it recognize the Flank compiler, and at the end, just to move forward, I just decided to, okay, I'm taking the output of Meson and I'm manually writing in the EasyBuild to patch out all the stuff that is not supported by Flank. Might be an easier solution once the Meson properly recognizes Flank, I guess. There are some libraries where there is actually no configure and you have to write your makefile, but that's, I guess, true for any toolchain. And unfortunately, I was not able to get CP2K to compile it because actually one of the features of CP2K is ends up hitting and not implemented in Flang. And actually, about these not implemented errors, there are 339 of them. So if you grab through the source code, this number didn't change between 20.1 and 0 and 1.1. Actually, the number I was just yesterday night as a comparison with 19. The curious thing, this number didn't go down from LLVM 19, it actually went up, which I guess it means there were just a lot of features that they didn't even think about Fortran, and now at least they know that they are not implemented in this version. And this is basically a list of all the to-dos. Basically, you can grep for this to-dos function, and if you hit them during your compilation, you will get an error. As you can see, there is still some stuff missing about OpenACC. There is some stuff missing about coarrays, and so on, basically. And as far as in terms of features implemented between GNU and Fortran, they are fairly similar. Both LLVM and GNU implement completely the standard for C++ 11 and 14, at least they declare they do. They are almost complete for the C++ 17 standard. Both LLVM and GNU have some still features flagged as missing on their table of features. LLVM seems to be slightly closer for the C++ 20 standard than the GNU one, but just in terms of feature missing, I haven't actually gone into the substance of the feature. Maybe there are some features that were more low-hanging fruit that I cannot really comment on that. And for the 2023 standard and the 2C, which should be the 2026 standard, they're still very much experimental or work in progress. Concerning the Fortran standard, the 1995 should be done in both GNU and LLVM. There is still, I think, one feature missing in the 2003 standard, but it is marked as done on the LLVM website, so I hope they're still working on this feature, or maybe they deem not it relevant. But both GNU and LLVM are marked as done. And for the 2008 standard, they both still missing like 5 to 7 features to implement, and the 2018 and 23 are still very much express. In terms of targets and feature and like target feature supports, I think this is where LLVM is starting to get the edge, especially on newer architecture compared to GCC. For example, we can see that the RISC-V target support by LLVM are actually much more than they were for GCC. And I know for sure that there is also been a lot of work done in the LLVM project to also have optimized scheduling model for the RISC-V. I assume this is also going on in GCC, but I couldn't find the status of it. In terms of where to go now, so what do we have now in the EasyBlock? What are we missing? We basically are compiling almost all of the upstream project. The only one that we are missing are the LLVM libc, which is actually still flagged as experimental because for now all these allow for static linking and not for dynamic linking. And I guess we could probably start to work on this when they remove the experimental flag and the build procedure for this is standardized. There is the libclc, which is the OpenSCL implementation, which I just didn't play around with them, but we can try to enable it and see if it works. There is LLVM libgcc, which is basically a compatibility layer between the glibc, the GCC standard library and the LLVM ones, which is not really that useful unless you are building an entire software stack for an operating system like Ubuntu releasing your software, but on top of the GCC. PSTL as a project actually was not very active, so I didn't try it yet to build it, but it's there. And then there is the Spear5, which is actually an external project that I started to play with last week, and this is basically to get to compile from LLVM IR to Spear. And this is also very useful in the, for example, in the SQL toolchain, if you're offloading. You can either go directly to machine code, but you can also compile to Spear5 intermediate representation. On the maintainability problem, for sure, we need more testing. We need to test more systems, especially with GPUs. We need to test cross compilation. This is something that I'm not really an expert with, so help here is very welcome. And also, we need to test probably the entire build matrix of parameters that we now support with the EasyBlock, because I can guarantee that the default one that the default parameter will compile and some other combination, but I cannot guarantee for all of them. I hope that they will work, at least they should, but they should be tested. Wrap up, okay. Yeah, in terms of other stuff to do, I guess there is only the Okay, the optimization flag, we should play more with it. And in terms of actually building a toolchain, there is a decision here to be made, and we can either build on top of what is already there for GCC core, and we reuse what is there for GCC core and just build with LLVM on top of it, or we start from scratch. The problem of building on top of GCC core is gonna be that we are gonna probably make sure that we don't have any GCC specific runtime being embedded into those binary or libraries, because if you actually do some testing, mixing for example, the OpenMP runtime with LLVM, libOMP and libGOMP, you actually get some undefined behaviors where libOMP does not behave as you would expect. Here, for example, we are not actually starting the thread in the main, but we are starting the one in the GCC compile one. And I guess also we should probably ban the libstd runtime library, because LLVM makes some claims about being API compatible with the GCC one, but not everywhere. So I guess we can expect some undefined behavior there as well. Thank you for your attention.
And we're over, and we can't be too far over today, so I don't think we're going to have time for questions now. We should have a little coffee break.
Davide's around for the whole
but you're here for the week, right? Yeah, so hopefully we'll catch up again.
Let's take a 15-minute coffee break, and then we resume 10 past the hour.